and for cloud geometry, it's stress medium G. So this was very nice, and so then it was verified in the liquid crystal experiment of Takeuchi and Shano. So here you see this is a circular geometry, and you get the trace medium GUE, and here it's a flat geometry, and you get the trace medium GOE distribution. This is the same liquid crystal experiment that we studied before. And so now the picture is, I come back to the same thing. So all these discrete growth models, not only the second moment, which is universal, but the full height distribution in all these models are universal. And they're the same as in the KPZ equation. And they're all described by the stress integral distribution in trigonometric set. So this was the sort of main story of which got over the three decades. And in 2016, KITP did a conference, and where this 30 years of KPZ equation was celebrated. So there are, of course, many other interesting open questions here. I mean, I did not talk about higher dimensions, and even in one dimension, if you have a finite size system, there's there's a lot of different physics which involves here. And so far, I was talking about an infinite system, just the growing part of the system. But in a finite system, you can have a steady state, and then you have a different physics, and not much is known about that. And in higher dimensions, nothing is known essentially. What is the height distribution? Nobody knows. So that's a wide open topic. And so in the last 10 minutes or so, I just want to talk about now our recent contributions to the subject, which is essentially that the KPZ and the cold atom system. Okay. So what do I mean by that? So cold atom, I mean, as all of us know now, by there have been spectacular experiments over the last decade to investigate essentially in atom physics, that you can actually investigate the interplay between quantum and statistical behaviors of many body systems at low temperatures, and you can actually investigate the interesting quantum many body effects even in absence of interactions. So, for instance, I mean, just by quantum statistics, for instance, for bosons, a spectacular measurement of Bose-Einstein condensation, and also for fermions, even though they are non-interacting, but there is still a Pauli exclusion principle. They are quantum particles, quantum statistics. So effectively there is some kind of repulsion between them, and this can also lead to reach quantum many body physics. So what we are interested in a problem very simple. So which is that just n non-interacting fermions. So I take n non-interacting fermions, and I put this laser trap, harmonic trap. It can be 1, 2, or higher dimensions, but let's focus on one dimension. So I have a harmonic trap, and I have this non-interacting fermions. So what happens here is that this harmonic trap and introduces a finite edge to the system, as we'll see in a minute, okay? Just like in the random matrix theory. And so now near the so this is the edge basically. They are confined in a finite region of space. Now inside the bulk, deep inside the bulk, where you don't see this potential, there it's just a traditional free electron system, so there's nothing big deal. It's a transcription invariant in the bulk here. But when you come to the edge, so out here, the traditional theory like LDA, local density approximation or Thomas-Fermi approximation works very well. But when you come to the edge, the mean field theory or this Thomas-Fermi theory cannot describe the edge physics, and you need to develop some new physics if you are interested. Because as I said, the number of fermions near the edge become very small. So the quantum and thermal fluctuations both play a dominant role. And to describe such fluctuations, you need new physics. And that's what we have been doing over the last few years. And what we find is that there is universal in the sense independent of the trapping potential, universal properties of the fermions near the edge as you zoom in and look at the edges. So, for example, I mean, I'll not give you the details, but just to tell you the main results. So, for instance, I mean, okay, so what is the problem you're looking at? So, I'm looking at n non-interacting fermions in a potential. So, my Hamiltonian many body system is just minus half del 2 del xi square, sum over I equal to 1, plus half in omega square, summation xi square. Okay? So, this is my Hamiltonian, and I'm interested in the many body ground state wave function of this system. So what is this? This is just a stator determinant. So if I know the single particle wave function, which all of you know from basic quantum mechanics, is the single particle wave functions phi kx is just e to the power minus some x squared, something here, and then you have these Hermite polynomials, right? So these are the different quantum states with energy levels which are k plus half h bar omega. So when I'm in the ground state, that means I have these energy levels, and you just occupy the first n levels up to the Fermi level. So that means you want to construct this stator determinant, n by n stator determinant, from the single particle wave functions with ij less than equal to n minus 1 greater than equal to 0. So you just take the first n single particle wave function and you construct the stator determinant out of that. That's your many body wave function. And if you take the mod of this guy square, so this is the quantum probability density, because these are quantum fluctuations, right? So at zero temperature, there is no quantum fluctuation, this is quantum fluctuation, and this is just the probability density of the particles to be at x1, x2, x3, xn. Now what happens is that if you just substitute this single particle and calculate this stator determinant, what you find is very nicely that this is just exponential minus xi square and times xi minus xj square. Okay, up to some normalization constant. So this is exactly same as the joint distribution of the eigenvalues of the GUE random matrix. Okay, so there is a one-to-one correspondence between the positions of the fermions and the eigenvalues of the GUE matrix. But here it's very physical. You see, this origin of this term in the random matrix theory was van der Waals determinant coming from the change of variables, Jacobian term. But here they are direct consequence of Pauli exclusion principle, because stator determinant tends to, it must go to 0 when any two rows and columns coincide. And so this is just a manifestation of Pauli exclusion principle. Okay? So once you have this mapping, and this was a very, very useful mapping, so the first thing that you predict is that if you look at the rightmost fermion at the ground state, which is just the largest eigenvalue, okay? So therefore, it should have also, once you properly subtract the mean and the width, it should have the tracing medium distribution. So this is our first prediction that the thanks to this simple mapping, that the rightmost particle at zero temperature fermion in this cold atom system should have the tracing medium distribution. So this will be direct. Also, this is the first. I don't know. This is a beautiful application of the random matrix eigenvalues. They're just the positions of the fermions. And then you can ask me, okay, what happens at finite temperature? So now I increase the temperature in the system, and I ask what's the distribution of the rightmost particle. So now I'm adding thermal fluctuations to it. Quantum plus thermal. So again, you can do the computations. I'm not going into the detail, but what you find is that this random variable now is related to the height of the KPZ equation. So so I have to first map it. So finite temperature in this problem corresponds to finite time in the KPZ equation by this exact identification. So zero temperature means very late time, and finite temperature or high temperature means short time. Okay? So I have to look at the height problem in the KPZ equation. Okay? So this is the random variable in the cold atom problem, rightmost fermion position. I have to subtract off its average value and divide by some width. So this is the random variable. So what I'm saying is that this random variable has the same statistical law as the height in the KPZ equation that you have just seen, plus some other object. This G is a just a random variable which has a Gumbel distribution, but these are details, never mind. Essentially, the height at finite time in the KPZ problem has the same distribution as the rightmost particle at finite temperature. At zero temperature, this corresponds to height at late time, which is tracing medium, but at finite time corresponds to finite temperature. So if I know the the KPZ problem, the height distribution, I can predict exactly what the distribution of the X max at finite temperature. And this is what we did in some recent studies. Again, I'm not sure of the details, but you can actually calculate precisely by borrowing the results from KPZ equation. You can actually show that the distribution of this guy at finite temperature has a precise. These are some polylogarithmic law and so on. But these are details. So what is the conclusion? So the conclusion is that at zero temperature, I mean, we know it's trace medium. Now, as I increase the temperature, the rightmost particles in this fermion problem, it crosses over from the trace medium to the Gumbel distribution. Because at very high temperature, it doesn't see the Pauli exclusion principle, so they are like independent fermions. So you go into so-called the Gumbel distribution of classical extreme thermal statistics, and you can actually work out the exact crossover between these two regimes. Okay, so let me just summarize and conclude my talk. So what I described to you is sort of a nice, story, a story of the evolution of the KPZ equation, starting from second moment all the way up to the full distribution. And what we have seen is that the full height distribution is universal in 1 plus 1 dimensional KPZ growth models, and is given by the trace medium distribution of random matrix theory. Now, trace medium by itself is also ubiquitous. It's not just in KPZ equation or growth problems. It appears in gauge theory, it appears in many other different problems. And so the recent application of this, that we looked at is the H physics in this cold fermions at finite temperature T, which is related to the KPZ problem, height distribution at finite time T. And the H fermions at the trap at 0 temperature, they provide that sort of exact physical relation of the Gaussian, the random matrix eigenvalues. So that's a very nice connection that we found. And of course, there are many interesting questions. We are collaborating with Christoph Salomon at Norman Superior, and also we're talking with Emmanuel Bloch at Munich to see if some of these predictions can be verified in the real experiments on the old atom systems, because they have this quantum microscope and other objects, sophisticated experiments. And then there are, of course, many other interesting questions, like, for example, the KPZ height distribution in the higher dimensions is a widely open problem, and what kind of university classes there will be, are there any random matrix instances there? So, okay, thank you very much.